Okay, I'm going to walk through a full system design of this sonar sensor, sonar sensing system, and a little bit how we used it with the oscilloscope and the RTL programming involved in it. Okay, so let's start with everything on this system revolves around a clock. We're using a 100 megahertz clock. That's 100 million ticks, which is a cycle, one clock cycle per minute, per second. That is 10 nanoseconds per cycle. The units of measurement we're going to be looking at are milliseconds, microseconds, and nanoseconds. Milliseconds are 1,000 times bigger than microseconds, and same with nanoseconds, 1,000 times bigger than those. All right, so the reason I'm telling you this is because this sensor, this right here is the ultrasonic transducer with the transmitter, and the receiver sends out a sonic pulse and receives a sonic pulse. This transducer runs on a 100, it requires a 100, or I think next 10 microseconds, 10 microsecond trigger to pulse. So this is in microseconds, but this is in nanoseconds. Now here's the flow. The design flow, we're going left to right, as you can see here. And I'll show you how each of these modules is implemented, starting with right now with the timing, which is the heartbeat of an FPGA. The main thing an FPGA does is count clock cycles, count timing, precisely. All right. So now what we're going to do is we're going to talk about the pulse width. The pulse width is clock cycles, the amount of clock cycles. So if the width is wide, you have more clock cycles. If it's narrow, you have less clock cycles. And we find that out with this on the oscilloscope when we plug this into the oscilloscope. So what you'll see is this will have two channels, channel 1 and channel 2. Channel 1's the trigger sending out the pulse out, and then channel 2 is the pulse is going in. And so the pulse, what I did is I take a book and go back and forth. The pulse width gets narrower because there's less clock cycles as it gets closer. It gets further away, the pulse width gets wider and wider, wider. There's more clock cycles. And that is seen on the oscilloscope. You can see that in my old videos. I did a video about that. Moving on. So, how do we get to the 10 microseconds trigger pulse? How do we delay that? We use counters. So a counter would just be, it's essentially like doing, you would do the math and just convert the nanoseconds to milliseconds. Smaller to bigger. Divide. Move them decimals place left. So you're just moving the decimal place 3 times. So that's how you implement the counters. And that will give us our pulse width. But We also need our pulse width to be in, this is your period length right here. The time, that's a period, that's a period, that's a period. This is a pulse. This is a pulse. The pulse is in microseconds, 10 microseconds. The period needs to be 100 milliseconds. The reason it's in milliseconds is because as the sonar burst goes out and the other one's being received, if you have that period in between going too fast, then you're going to have too many signals. Before this signal comes back, another signal is coming out. So you will have corrupt data. So you have to set the period right here to using counters to 100 milliseconds. So that's what you do with in the pulse width. Use counters, set the timing for pulse, or excuse me, for period and pulse. All right. Now that we have that, now this is also, these are connected with a wire. Now, once this signal goes out, we're at the producer stage. The producer stage is where we start our echo timer. The echo timer is going to start like a stopwatch as soon as this pulse comes out. The echo timer starts, signal goes high. And it'll start counting clock cycles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it'll stop. It'll go low when the echo is received. So that is our producer. That is the echo timer. Now that clock cycle is a 32-bit. 32-bit count. That 32-bit count will now go to be stored in the FIFO buffer, first in, first out buffer. When write enable is high, this is what the function is. This is what the function is. When write enable is high, meaning writing data, and the FIFO is not full. Because you don't want to write, if you're sending data, but this buffer, this is, it can't store any more bits. You can't have that. So this is why we implement the write enable, the pointers. That's the main function of a FIFO buffer, is the read and write. It's writing in data, and this is reading out. Same time, checking if it's full, checking if it's empty. Now, and the reason why you need a buffer too is because if I add another sensor here, so now we have two sensors. You have two sensors. That means you have multiple pulses coming out, multiple coming in. And again, if they arrive at the same time, then the data becomes corrupt. So that's why we need a buffer to store that. Now we get to the consumer. This is where we're going to use our first FSM state machine. The consumer is going to implement packet framing. I'll show you what that is now. Packet framing. We have 32 bits. We need to convert to 5 bytes, which is 40 bits. So it's enough so that it can hold. So we needed an identifier for packet 1, packet 2, and then we do 2, 3, 4. So there's packet 1, 2, 1, 2. Ay, ay, ay. There's our 5 packets. The reason why you do this is because you need to have, with this data streaming out, if it was just like, you'd see 3, 3, 2, 1, maybe that was the data. But if I don't have an identifier, without identifier, after the signal arrives in software, the identifier, without the identifier, it might read like 1, 3, 2, 0 out of order. So that's the purpose of having your packet framing with the finite state machine. The state machine, you use a state machine when you have multiple steps. You want to track your progress. So like a stoplight, like a traffic light. You have stop, red is stop, yellow's go, caution, green is go. So that's why we have that's what we'll be doing our consumer. That signal now has to be serialized. And it goes to the UART, the Universal Asynchronous Receiver Transmitter. So this data needs to be serialized. So again, we need another FSM, because last time we needed steps to take the packet. We needed to order the packets with the identifier being first and 1, 2, 3. So each step had to be ordered. Now we have to take those packets and serialize them. So 1 byte, 8 bits. Now we've got to need a start bit. We need the data bit and the stop bit. Serialized means bit by bit. transferred bit by bit, individually. Can't send 2 bits at once. So it's rate limited. Individual. So that is how the UART works. So at this time, everything is occurring. Everything we've been doing occurs in the FPGA. Now, that serialized data, it gets unserialized, if that's the word, in the chip. But we're not going to worry about that. That's not something that I do. It's in the hardware. But now that UART is transmitted to the Linux machine, to Python, to software. So we're going to solve for the physics and software. Everything else, we were doing timing in the FPGA. Now we do the physics, like, for example, the speed of sound is 342 meters per second, and you have to convert that to centimeters. Round trip. Because the pulse goes out and it comes back in. So convert to centimeters. And we use the megahertz. So you divide it by the megahertz, which is 100 million hertz per second. Let me think what else we're doing in the Python. Take a quick look. Hold on. Yep, that's it. So yeah, we take those clock cycles from the FPGA. The clock cycles is the timing. And then in Python software, we convert that to centimeters. So you'll see, instead of just a pulse width before, whenever you would see the book in my other videos, you'd see the pulse width on the oscilloscope. You just see it getting wider and narrower, which are clock cycles. Now it goes 10 centimeters, 8 centimeters, 3 centimeters, 1 centimeter. So that is the full flow of a Sonar sensor on an FPGA written from scratch. Deuces.